everybody, it is I, your all-time favorite chemist, Richard Blyle, here once again to provide another chemistry lesson while completely nude from the waist down. Listen, a very good friend of mine actually made a comment to me some months ago that he felt like, he's surprised I'm not a chemist, that I don't teach chemistry, that I'm not a chemistry professor. I am. Or I was. I was a tenured full professor, although for some reason they spelt fool with two O's, a tenured full professor at a state university in South Dakota. I would tell you which one, because it's really a very good institution. It has amazing faculty. It is far better than an institution of that size should be, but the problem is I was wearing one of their sweaters when doing a stand-up routine. I posted a video online, and their attorneys asked me to never ever be associated with them in public again. So I didn't think the routine was all that bad, but there it is. So I suppose we should give it some kind of a name. Let's call it, I'm going to make up some initials here. Let's call it, I don't know, FU. So the reality is that I have my PhD. Actually, as an undergraduate, I went to the University of Cincinnati in Ohio, just an incredible school. They have incredible engineering, great music conservatory that is just incredible, wonderful, wonderful institution, great state school. Give me my launch. They're very powerful. They're very, very good. They're not like the huge name in Ohio, but they are outstanding. From there, well, of course, I worked in industry for a couple of years. I went to Boston College, where I got my PhD, which is right here. My PhD is in, well, if you read it, it's just chemistry, but I studied theoretical chemistry, statistical thermodynamics to be precise, which is why I know a little bit about quantum and classical thermodynamics. Statistical thermodynamics bridges the two. It is an Ivy League school, private school, it's Catholic, and the Jesuit priests there were just fabulous to work with. They were so much fun. I just adored them. So that was definitely very, very cool. I studied, I did research at Harvard University as a visiting scientist. I had research projects at with one of the professors at Princeton University. While I was working at the Mount Sinai School of Medicine, which is a Hasidic Jewish institution. It's a hospital, it's a teaching hospital, but they also have a chemistry and theoretical chemistry section. I did research at Purdue University as a postdoc, which was very cool. And of course you all know Purdue. My first teaching gig was the Kettering College of Medical Arts in Ohio. If you started your car and you didn't have to crank that crank, you can thank Charles Kettering for that. He is the one who invented the electric starter. And from that he built the Kettering Medical Center, and part of that is the Kettering College of Medical Arts, which is just fabulous institution. Again, very small college, but very powerful, and very good education. And then I went to, well, FU. So I'm not going to mention them because, F you. So anyway, today we're doing, now there's a little different, just a little different. Today's lecture is called Organic Chemistry for the Organically Challenged. Here's the backdrop, the backstory on that. When I took organic chemistry, I almost failed. Organic chemistry is considered the weed out course for a lot of chemistry programs, and for good reason. And I don't like the way they taught it. I should have probably failed, but I figured something out late in the year, not soon enough to save my grade, but enough to let me pass. The way they taught it, they gave me this 1,300-page book, and they said, "Here, memorize this, we're having a test." Well, I suck at memorization. I'm just not good at it. So I didn't do well. But late in the year I realized, you know what? It may be organic, but it's still chemistry. So this lecture today, usually most of my work I do here is for a general audience. I cover some heavy topics, some really late topics that you know should have a lot of background. But I try to cover them in depth enough that people with the background to understand can get something out of it, at least something to think about. But I also try to cover it in such a way that for people who have no background, they can at least understand, follow along, and they get something out of it too. This time, I am specifically addressing students who have taken the first year of chemistry and are now facing their second year, which is typically organic chemistry. We're going to talk a little bit about the chemistry behind organic chemistry. Now, I wrote up a little document shortly after that. I had friends that were still facing it, and I wrote this little document, which I entitled, this is from the 80s. This is an old document. And I called it Organic Chemistry for the Organically Challenged, and I am going to be doing something different. I'm going to be referencing this today. Usually I don't use reference materials, but I'm going to be referencing that. You're welcome to watch. If you're not in chemistry, you're welcome to watch. You may learn something out of it anyway, but it's going to get technical, so be a little careful. Beware. If you're facing organic chemistry, if you think the way that I do, you will hopefully get something out of this. If you don't think the way I do, this is going to be a waste of time. But worst case scenario, it'll be nothing but a waste of time. You may waste, I don't know how long this video is going to be, you may waste 40, 45 minutes. That's the worst of it. I mean, if you've ever seen a bad movie, you're going to waste less time on this than that bad movie. So let's talk about organic chemistry. I am going to give a little bit of a background as well. I am again working 2 cameras. What did I just do? Am I still recording? I am still recording. I'm working 2 cameras because, like I said in my Mexican meat video, I worked 1 camera before and I lost everything. So I'm working 2 cameras, so if one of these fails, the other one will hopefully not. So if sometimes I'm looking at you, that means I'm looking at the camera that I'm posting online. If I'm looking like I'm looking away, I'm working on the other one, posted the other one. Either way, we should have a video to post by the end of this. Organic chemistry, a little bit of background. Organic, it's called organic because of a theory called the vitalism theory. The vitalism theory many years ago, before chemistry became such a huge discipline, stated that organic compounds, which are basically compounds with carbon and hydrogen, there's some weird exceptions both directions, organic chemistry compounds can only be created by the action of something living. In other words, microorganisms in their metabolic processes can create organic compounds, but in a laboratory you cannot. That vitalism theory was actually disproven by Adolf von Baer, who made an amazing discovery. He was trying to do a reaction that he was sure would create an inorganic compound, and he accidentally ended up with an organic compound. He used ammonia and carbon monoxide. I forget what exactly he was trying to create, but he ended up creating the breakthrough compound, the amazing chemical, the organic chemical created strictly by an inorganic reaction. That incredible organic compound was urea. Yeah, found in urine. So, you know, humble beginnings, you know how it goes. But here's the thing. Organic chemistry is one of the most versatile chemistries, well, it's the most versatile chemistries anywhere. If you ever look up compounds, there are hundreds of thousands of times organic compounds than there are inorganic. That's because carbon is nature's tinker toy. It's nature's Lego. Carbon has 4 electrons around it, all of them called, and this is where we're assuming you're going to know something here. I'm talking about Lewis dot structures. Carbon has 4 valence shell bonding electrons. Now, it's not the only one, but you know full well, I hope, that chemical bonds always involve 2 and only 2 electrons, one from each element being bonded. So this carbon is contributing 1 electron, this carbon is contributing 1 electron. So there are 2 electrons that are shared. We denote that it is shared with this straight line here. Now, you can have double bonds and triple bonds. So we can actually get, for example, a second bond here if we want to. And now all of a sudden there are 4 electrons being shared between the 2 carbons. But the thing is, each of these bonds is still only 2 electrons. So yes, there are 2 bonds there, but each bond has only 2 electrons being shared. This second bond, now the double bond or the triple bond is stronger than the double bond. The double bond is stronger than the single bond. They add, those strengths add. So that's not a surprise, but something that's going to come into play here. The second and the third bond, not the double bond collectively, but this second bond here is weaker than the original bond. The strengths add, but the second bond is always weaker than the first bond, and the third bond is about the same strength as the second bond, maybe a little bit weaker still. Now here's the amazing thing here. So one reason that there are so many organic compounds is because carbon can form 4 bonds. So you can go off in any direction you want here. We can put another carbon down here if we want. And we can make this chain as complicated as we want with carbons. You'll notice a lot of unpaired electrons up there. Those unpaired electrons would eventually end up with hydrogens. But I'm just building the compound now. Now, of course, we can also share electrons with other elements, like this. I'm going to do something. Actually, let's put this one here. Okay. Now here's the other reason organic chemistry, why though there are so many different possible compounds. This carbon-carbon single bond here is roughly the same strength as the single bond between carbon and any other element. That is exceptionally rare. In fact, carbon is the only one that does it. Most of the time, when you have a single bond between 2 of the same types of element, these bonds are exceptionally weak. That is very, very weak. That means that you cannot have a chain of oxygens. Because eventually, well, let's put it this way. This is called a peroxide bond. Peroxides are extremely reactive. so reactive that they cause damage to DNA. And your body has developed an enzyme called peroxidase that literally seeks out and attacks that oxygen-oxygen single bond. This is why, if you've ever used hydrogen peroxide to kill bacteria on a wound, it will do it. It's also fizzing because of your peroxidase breaking this down into oxygen. This bond is so weak that aside from hydrogen peroxide, most peroxide compounds, like benzoyl peroxide, which you may have heard of, most peroxide compounds are actually explosive. They are so weak, they are so desperate to react that they just react first chance they get. But the carbon-carbon single bond is very stable. That means that I can make this carbon-carbon chain as long as I want. This is what polymers are. They're very long carbon chains. And we can throw other elements in there if we want. But the carbon-carbon single bond is extremely long. And carbon can make 4 of them. That's incredibly powerful. How long can we make them? There's a protein in your body called the titin protein. In your body, right now. That protein is over 300,000 atoms long. A chain, a single molecule, a chain, 300,000 carbons and nitrogens long. That's a big molecule. So yes, the carbon-carbon bond is exceptionally versatile. Okay, so there's a little bit of background for you. By the way, yeah, we're not going to cover that in this video. You'll learn that in class. There's a shorthand notation for organic compounds. You'll talk about that in class. Get used to that shorthand notation. Now, here's the thing. If you understand the principles of chemistry, you can get rid, I found that 60-70% of the memorization disappears because it makes sense if you just understand what it's doing. Okay. Finish that one. Did that one. That's done. Okay. The interesting thing in chemistry, though, is not the carbon-carbon single bonds. Because there's not much you can really do with those. Those are very stable, they're very happy. You can react them, but it's not easy to do, so for the most part they don't do a whole lot. What we call functional groups, pardon my voice, puberty, you know. It's the functional groups where the interesting chemistry occurs. Because anytime you have anything other than carbon-carbon, and that includes double and triple bonds, anytime you have anything other than carbon-carbon single bonds, interesting chemistry can happen. For example, I love fat. That fat-free ice cream you can get, I don't want that crap. I want the ice cream where they add the extra fat that they took out from all the fat-free stuff. That's the ice cream I want. I don't want it flavorful. The difference between a fat and an oil, oils are liquid at room temperature. Fats are solid at room temperature. Technically, that's the only difference. But the reason fats are solid is because it's all carbon-carbon single bonds. It's called saturated. Your body can't do anything with that. Unsaturated fats, which is oils, have at least one carbon-carbon double bond. And like I said, that second bond is weaker, so it's easy to attack that second bond and turn that oil into something more useful for the body. But if there are no double bonds, your body doesn't know what to do with it. So Let's turn it into cholesterol. Yeah, we'll make it cholesterol, put it by the heart. We'll get it to the heart, and we'll just get to it later. We'll just put it right by the heart. No big drop, no problem, just store it there. That's why I had a heart attack at 47. Hey, my anniversary of my heart surgery is coming up, too. Yeah, I've been dead. Okay. Never so dead as when I was married, though. So anyway, anytime you see anything other than carbon-carbon single bonds, those are functional groups. Now, here's where memorization comes in. Whether you know this stuff or not, you have to memorize the functional groups. You have to memorize what they are. You have to know the difference between a ketone and an aldehyde. You have to know the difference between an amine and a amide. There's nothing you can really do about that. Nomenclature, get ready for it. You just have to memorize it. But the properties, the physical, the chemical reactions, those you can understand using basic chemical knowledge. And that's really what we're talking about today. So, one of the more important concepts that you learned is polarity. Polarity, based on the polar scale. What was that guy's name? Oh, he was brilliant. Okay, anyway, it'll come to me. Remember, and there's not a lot of polarity you need to memorize. You don't need to memorize the exact numbers. But Pauling's electronegativity scale. If you look at the Pauling electronegativity scale, you will see that the electronegativity of hydrogen is approximately equal to the electronegativity of carbon. That means that when you have carbon-hydrogen, the electrons in that bond are shared more or less equally between the carbon and the hydrogen. They are shared equally. However, the electronegativity of carbon is less, and quite a bit less, than the electronegativity of oxygen, the electronegativity of nitrogen, and the electronegativity of most of the halogens. I'm putting an X here. This is organic notation. X stands for fluorine, chlorine, bromine, the halogens. That means that the electrons are not shared equally between carbon and oxygen. The electrons, which is really just, it's a cloud, and it's like they're shared between oxygen and carbon, but not equally, because they like oxygen better. They might go over and visit carbon every once in a while, but they're going to spend most of their time here around oxygen. This creates not a full charge. This creates what we call a partial charge. The electrons, which remember, the electrons are always negatively charged. So the electrons are spending more time around the oxygen, giving it a partial negative charge. A partial negative charge. It's a pretty strong partial negative charge. The carbon, on the other hand, ends up with a partial positive charge because its electrons are spending too much time over here at their Aunt Vicky's. So it's partial positive because they're happy to be rid of those damn kids just for a little bit. Keep in mind, this becomes important for a couple of reasons. First of all, oops, I did do that on the end. Missing an electron. Keep in mind, opposites attract. So for example, let's consider what a lone pair of electrons are. These are called non-bonding or lone pair electrons. They're happy. Anytime you have two electrons, they live in what we call an orbital. This is a molecular orbital between carbon and carbon. There's an orbital that is formed from two atomic orbitals, and that molecular orbital is where the two shared electrons live. They live in this orbital right here. It's all an orbital is a region of space where you're going to find electrons. That's all an orbital is. It's just where you're most likely, not where you will find, it's where you're most likely to find those electrons. So a lone pair is two electrons that come in already paired. Well, if they're already paired and you can only have two electrons in a bond, it's because you can only have two electrons in an orbital, this is not going to bond. It's a non-bonding electron pair, or a lone pair. But they live in an orbital as well. They live in an atomic orbital. And again, an orbital is just a region of space where you are most likely to find electrons. That means that this lone pair here, all that really represents is a region of space near the oxygen occupied mostly by electrons. And electrons are negatively charged. So a lone pair is basically a negatively charged region of space. All it is. This is negatively charged region of space. Where is this region of space? If we put another, let's put a water down here. Water is a bent molecule, has two lone pair of electrons. So if we look at, say, this pair of electrons here, lone pair of electrons, what is that going to be attracted to? Is this lone pair of electrons going to be attracted to the partial negative oxygen or the partial positive carbon? Well, that orbital has a negative characteristic to it. It's not charged. It has a negative characteristic. It's going to be repelled by the partial negative oxygen. It's going to be attracted to that carbon right there. That is a big part of organic chemistry reactions and biochemistry reactions. We see this a lot in biochemistry reactions. It's just a lone pair of electrons or a negatively charged ion, or something with a partial negative charge being attracted to the opposite charge on the molecule. That is going to be so important. Now, I'm going to erase this because this is getting too complicated. Let's simplify things. So in your mind, just kind of keep a little list of electronegativities. Or is it about the same, or which one is a little more electronegative, which one is more electronegative than the other? I put together this thing using a simple reaction. And what we're talking about, this is called Mechanistic Organic Chemistry. This is the chemistry that I took 2 years after I figured it out on my own in organic chemistry. Why don't they teach this in organic chemistry? I don't know. They cover it. They review general chemistry, and then they kind of pretend like, okay, now you can forget all that. Well, no, don't. It's important. It is just as important as pronouncing the first letter T in the word important. Okay. So, in my little document, here is the chemical reaction that I used as an example. So we're going to take formaldehyde. This is the organic structure for formaldehyde, and attack it with ethylamine. Ethylamine you're going to see why this is called electron pushing here. How is this going to react? Well, the nitrogen on ethylamine has a lone pair of electrons. I think I want a new piece of chalk. Yeah, I'll use this one. Okay. I'm surprised that chalk hasn't fallen down off the blackboard yet. Has a lone pair of electrons. Region of negative characteristic. Not a negative charge, negative characteristic. We also know oxygen is more electronegative than carbon, so we know we have a partial negative carbon, a partial positive carbon, partial negative oxygen. Is that lone pair of electrons going to attack the oxygen or the carbon? Well, the oxygen is negative, so are the lone pair electrons. So of course, the attack will be on the carbon. Now, if we form a bond between carbon and nitrogen, notice that carbon has 4 bonds. That's all it's allowed to have. It is not allowed to have any more than 4 bonds. So if we're going to form a bond there, we have to find a way for that carbon to make space for the new bond. This is called electron pushing. Remember what I told you. In a double bond, the second bond is always weaker than the first bond. So what can we do? If we're going to take and make a bond here between nitrogen and carbon, we can make room by moving the second bond. And by the way, it doesn't matter if you use left or right. This is all a cartoon. It's no big deal. But we can move that second bond out of the way and give the electrons to the oxygen. Like that. It's called electron pushing. And what we're going to form now, we have created a new carbon-nitrogen bond. We still have these 2 hydrogens. I'm going to just splay them out a little bit because now we have the nitrogen on the bottom. Now we have a single bond between oxygen and carbon. Now carbon already had 2 lone pair electrons, if you don't erase them. Those 2 lone pair electrons are still there. 1, 2. But now we have moved this bond up to the oxygen. It's no longer a bond. But that bond has 2 electrons, just like lone pair electrons. So we're moving 2 electrons. When we move those and place them on the oxygen, we're going to form a 3rd lone pair electrons like this. A 3rd lone pair electrons. Now if you look at this, you might think, wait a minute, that doesn't look quite right. If you know your chemistry, it's not quite right. This is where we talk about what's called formal charge. Well, if you heard that, I apologize. I just farted. Oh, the smell! Lord! I gotta see a doctor. Okay, oxygen. Formal charge. Oxygen has, if you look at the periodic chart, oxygen has 6 valence shell electrons. How many electrons does it have here? Well, when calculating formal charge, we have 6 that we started with. Every lone pair is 2 electrons that we assign to the oxygen. Every bond, 1 of the 2 electrons we assign to each of the 2 elements. So here, this oxygen here has 2 lone pairs, which is 4. and 2 bonds. So 1 electron from this bond, 1 electron from this bond. Gives us 2 electrons. The formal charge is 0. Look at this. We have 6 electrons. 3 lone pairs, which gives us 6 electrons plus 1 bond. We have a formal charge of -1. We cannot leave that formal charge in the final compound. But for this one, and this is just an intermediate, we have a formal charge of -1. I'm going to let you do the nitrogen. And if you do it correctly, you will discover that nitrogen has a formal charge of +1. A formal charge of +1. We need to get rid of these formal charges. We need it to be neutral. That gives rise to what's called a leaving group. Leaving group are things that are happy on their own. Think about halogens, for example. Halogens, chlorine, fluorine, bromine, we very frequently see them as -1 ions. They are good leaving groups because they're going to fly off on their own, and they're happy to do it. That's a good leaving group. Carbon, this oxygen here, this oxygen is not a good leaving group. How often have you seen an oxygen with a -1 charge? Not a good leaving group. So we look for a good leaving group. Remember your acids and bases. Hydrogen is actually a good leaving group. We know that hydrogen will be happy leaving with a +1 charge. Now if hydrogen leaves with this +1 charge, that means that both of these electrons are going to go to the nitrogen. And that hydrogen is going to take that +1 charge with it. But look, a hydrogen with a +1 charge, that'll be attracted to one of these lone pair electrons, won't it? So it's going to bring its positivity here. By the way, often we put charges like this in circles to denote formal charges. That hydrogen will be happy to take up one of those lone pair electrons. So we're losing a hydrogen, we're gaining a hydrogen, just in a different location. By the way, this species is called a Zwitter ion. Zwitter from German meaning opposite. Means that you have 2 charges on this molecule, but they're opposite charges. You have a positive and a negative, so the net charge on the molecule is still 0. And lo and behold, what we get for our final product? Remember, now one of those lone pair electrons is a bond with the new hydrogen that has moved. It's not the same hydrogen, but it picked it up in the same solution. And down here we lost one of those hydrogens. So where that hydrogen was, we now have a lone pair electron. When doing organic chemistry, look for leaving groups. Look for leaving groups, look to push electrons, look to where the charges are. That's going to help walk you through and understand many organic reactions that you are now faced with. And instead of memorizing them the way I tried to and failed, you'll be able to figure them out. And if you figure them out, it's locked in. You've got it. Look and ask yourself, why is this reaction doing what it's doing? And if you think the way I do, that is going to help you to memorize, and at least reduce memorization. Now real quick, let's talk about another. This is a very, very important reaction in biochemistry. And we're going to talk about another type of leaving group. If we have a protein, now, only have a couple more things to do. If we have a protein, in organic chemistry, R represents the rest of the molecule. Sometimes we're going to have a molecule so long we don't want to write it out completely. So we're going to use R, which just means and everything else, the rest of it. A protein is made up of a peptide. Now, you can do this, by the way, with DNA as well. You'll see that it's there. This is peptide. The difference, I'm sorry, not a peptide. This is an amino acid. The only difference between one amino acid and the other is the identity of this R group down here, which I put a dash by it to say it's different than this one. Let's react it with another amino acid. Like this. I guess I should be putting in lone pair electrons. I don't always. So bond there. There. Purists will be happy now. But look at this. I can circle this. What does that look like to you? Well, think about this for a second. What I just circled is 2 hydrogens and 1 oxygen. 2 hydrogens and 1 oxygen. This is called a dehydration reaction. The dehydration reaction is how proteins are created. It's also how DNA and RNA are created, is with dehydration. So our leaving group actually becomes water. Now we've just extended our molecule. We've added this amino acid to this peptide or protein or whatever it is. And look, when we do that, we still have this hydroxide end. We just moved it down. Which means we can do what? We can take another amino acid and add it to this one. And so on, and so on, and so on. Leaving groups. In this case, it just happens to be water. Okay. You're going to learn other things. If you form a carbon ring, for example, you'll discover the carbon rings of 5 or 6 are most stable. Other carbon rings exist, but they're not usually as stable. So always, if you can create 5 or 6 carbon rings, one last thing that you need to understand is called resonance. This is very important. Resonance. Now I chose a very specific example for this in my paper. So, this is a real these are all real organic compounds, folks. They may not be available commercially, or they may be. Actually, a lot of them are. That's wrong. I didn't do that right. I didn't do that right. Let me fix it. I apologize. I need another carbon here. Put that double bond down one. There we go. Now, this is an internal reaction. This is called an elimination reaction. We're going to lose water. Again, we have a really good leaving group because we have a hydroxide here and a hydrogen. If we take this away, we're going to take one of the, it doesn't matter which one. Let's take this bond and move it down to form a double bond. This bond will attack the hydrogen to take off water. I'm covering this quickly because in class you will cover it more slowly, more carefully. But having heard this, I'm hoping that I need a hydrogen here. I'm hoping that some of this will ring a bell when you hear it and you'll think, oh, that's what he was talking about in that video. And of course, feel free to come back and revisit this video as it does. But anyway, if we take that water away, we're going to form a double bond between this carbon and this one coming from this hydrogen. But that's not the only possibility, is it? Because I just as easily could have circled this water molecule on this side. Now this lone pair, this hydrogen is going to form the double bond. Sorry, that bond is going to form the double bond here. And we're going to form the water here. Taking this away, yada, yada, yada. So there are two possibilities. Both of them dehydration reactions. Where we get two different compounds. This is kind of an interesting song. This is called Wah Wah by John Lennon. He's complaining about somebody, and I think I know who, but I heard it was the other. One of his band members who was just complaining too much. Like, wah, wah, why are you crying kind of a thing. Which one of these is correct? The way to choose, look for resonance. Resonance stabilization energy adds roughly 13 kilocalories per mole of energy. And to have resonance, you have to have consecutive double, single, double bonds. You'll see this in benzene. That's why benzene is so stable. Double, single, double. This allows you to create resonance. Here we have double, single, single, double. This double bond is too far away to have resonance, so it will not happen. Therefore, this is the wrong product, and this is the right product. Well, what is resonance? Well, resonance, do I have room to write this down here? I think so. You denote resonance with a double-headed arrow. Notice this is different than the equilibrium arrow, which are two half arrows. This is a full resonance. Every bond represents 2 electrons, and we can split those up. So let's take one electron from here and move it here. The other electron we're going to put onto this carbon. There are going to be a lot of reactions where you're going to be able to do this, so you will see it in other places as well. We can do the same thing here. Take one of these 2 electrons and take the other one and move it onto this carbon. This will form a very unstable but real resonant form. Most of the time, the resonant form that you're going to see is not this one, but now this carbon has picked up one electron here. This was a double bond, now it's a single bond because we've given two of the electrons away. Again, one of these electrons is now going to this carbon, this, and we still have the CH3 group on the end. Anytime you have an unpaired electron, that is called a free radical. They are very unstable. They are highly energetic and reactive. If you don't believe me, stick your finger in a flame, because flames are basically gaseous free radicals, and you're going to burn yourself because they're looking for something to pair those up. But as a resonance structure, it means there's an alternative. This molecule can actually spread those electrons around a little bit. That's where resonance stabilization energy comes from, spreading around those electrons so that they're not all stuck in one place. It kind of has a choice. Polarity, double bonds, lone pair electrons, formal charges, resonance structures, and just remembering that rings want to be 5 or 6 rings round. And that's it. I hope these tricks really help you to reduce some of the memorization that you are stuck with in organic chemistry. If not, thank you for your attention. I'm sorry I wasted your time. But I've had some people, some former students say that this has saved their bacon. I've had others tell me it's a complete waste of time. I hope you find it useful. And it's something just to keep an eye out for in those organic chemistry chapters. Figure out why things are reacting the way they're reacting. Maybe it'll help you to reduce the memorization. As for me, I am